Okay, all right. Welcome back, everyone. Let's get started. Today is lecture 13, and we are continuing our discussion on unsupervised deep learning models. And more specifically, I'll talk about generative adversarial networks, or GANs, as they are more popularly known as, and some of the applications of GANs, some of the variations of the GAN model. But we'll most likely we'll try to understand the architecture and how we train these networks and why on earth we need these networks, right? And I would say this is an extension of our discussion of variational encoders, if you remember from the previous lecture, where we had an encoder decoder type of structure, but they were different. Like the variational encoders were different from the autoencoders in the sense that we were trying to learn the probability distribution in some sense, because we were trying to learn the mean vectors and the standard deviation vectors, and then we were trying to sample from them and then generate maybe new points. So it's the same idea here, where we will have two different networks and we'll try to do something with them. And that's why these are known as, and there will be a slight, I would say, difference in the variational encoders versus GANs, because the way we train them and the objective is completely different. So that's the lecture for today. And before I actually go and introduce generative adversarial networks, or GANs, I wanted to talk about two learning models in general. And more we have looked at those types of models until now many times. But let's look at them from the perspective of what exactly are we trying to learn and what exactly are we trying to output, okay? So generally speaking, if we come down here, there are two types of learning models, right? Of course, there are many different paradigms of learning, as we know. There is this unsupervised and supervised, and then there are different types of problems we are trying to solve. And then there is this difference between machine learning and AI. But then there are two different types of learning models, broadly speaking. The first one are known as, more generally speaking, they're known as discriminative models, right? So I'm talking about models that try to directly estimate the conditional probability of some y, some label y, given x, right? In supervised learning, or sometimes even in unsupervised learning, where I'm trying to find the conditional probability of some output given an input, right? So that's the first type of model. Logistic regression, in some ways, is that it's a discriminative model, because I'm trying to learn this label y given some feature x. And so essentially what I'm trying to do in a discriminative model is I'm trying to discriminate amongst various classes, right? So that's what this is telling us. Given an input x, what is going to be my label y? And then obviously I'm going to learn from some given labels and some given data, right? That's one example of discriminative model. And then there are generative models. And I would say high level, we saw, just give me a second. People who are online, can you hear me? I totally forgot to ask you guys. Okay, thank you, Mason. Excellent. Thanks, George. Yeah, because sometimes I just keep talking, and then after 10 minutes, I come to know that nobody was listening to me. Yeah, so going back to the two different types of models, if you remember, let me quickly go over what variational autoencoders did, is that I had some input x, and I'm trying to generate some output x hat, right? And then I'm taking this input and I'm deriving some mean vectors and some standard deviations. And then I'm trying to sample from them. So let's say I have a z. And then after sampling from that, I'm creating this x hat. And this was a high level how variational autoencoders were working. So if we think about this was the encoder and this was the decoder, right? And in some ways, if you just focus on the decoder part, I'm continuously sampling from this z, right? And then I'm creating a new probability distribution. That's what I'm doing essentially, right? And so in some ways, in a variational autoencoder, right, or a VAE, this decoder can be thought of as some form of a generator. Right? It's generating some output based on some input probability distribution, but it's not discriminating between different classes. it's generating a whole new output, right? And that output like might be very different from this, but it is deriving properties from that, of course. Like it is deriving its properties from X. It might be different. It might have new points. It might have some similar points. But the whole idea is that it's generating something. So in some sense, the second part of a variational autoencoder is very similar to a generator. And that's where the idea of like a generator comes in. And that's like, we'll see there are certain differences as well when we look at the GAN architecture. But that's the fundamental idea of a generator. That's one example. The other example of a generator type model is the naive Bayes classifier. I'm sure like many of you are familiar with it, many of you are not, but we'll go over that like quickly to just review what that is, right? And so what we do is we actually come up with a conditional probability for different classes based on some input values. And what like it's a simple technique for constructing this classifier, right? And what we're doing is we assign class labels to some different instances, and then we want to summarize the overall probability distribution of that. Okay, that's a lot of information. And of course, I have like given the details of this, but I'll quickly go over what we are doing in a naive Bayes classifier. And let's look at it from the perspective of a very simple problem and a very common machine learning problem where you have like, you're trying to create a spam filter, right? So you have like these emails coming in, and like, you know that from your own experience, when an email comes in, and if it has words like free or like sometimes Bitcoin, I've noticed that a lot. Those are usually spam, right? So maybe like one way to filtering out spam messages is that you can create your own filter and say that whenever I see these keywords, then I just like filter them out. Right? That could be one way of like dealing with them. So you're creating a filter rule. But then if I have like hard coded that like that filter, then what happens is sometimes those words might appear in like legit messages and they are also filtered out. And so that's why we need to create a machine learning model to filter those out. And the way we do that is by using this naive Bayes classifier. So basically, like if I would like, if I can come up with these words that can be found in spam messages, I can like call them like X. And so that they could be like free, I don't know, Bitcoin, what else? Stocks sometimes, and so on, right? So I figured like these are the words that might appear in like spam messages. And so my goal here would be to find like what is the probability of a particular message being spam given some input message X, which might have like some words, right? So that's the problem that this like naive Bayes classifier tries to solve. And so more generally speaking, like if you're not just looking at what, like two classes, spam or ham, we can look for like, let's say k different outcomes or k classes, right? So the problem that we are trying to solve is that what is the probability of getting some kf class given this input like x1, x2, and so on up to xn, right? That's the more generic form of this Bayes classifier. And in order to find, like in order to compute this conditional probability, we usually use the Bayes theorem, and I'm sure you're familiar with that, right? So we can write this thing as the probability of spam times the probability of X, which is like a vector of all these words, let's say, given spam, and then the probability of the total probability of all the words together in some ways. And so if you remember from your any like statistics or probability class, this thing is a prior, if I remember correctly. And then this is the likelihood. And this is the evidence that I have. Right. So then based on this, I can figure out whether or like given some input message with some words, I can figure out whether an email is a spam or a ham, depending on the probability values, right? So then how do I compute, like looking at this, maybe I can figure out like prior all spam messages, right? I can find the total probability of that. Maybe I can figure this out. But how do I figure this conditional probability out? And this numerator, actually, if you look at this numerator as a whole, right, it's in some ways, it's like it's equivalent to a conditional or a joint probability of something like this. Let me just remove this. And so what we're looking at here in the numerator only is a joint probability distribution of spam or not, right? And then all the input words. And you know that if I'm trying to compute this using chain rule from probability, right, I will be finding the conditional probability of each of these conditioned on the rest of the elements, right? And so it's going to be like huge, right? So like one way of writing this could be like I'll have probability of getting word 1, given word 2, word 3, and so on, and given that it's like spam. And then I'll have the probability of x2 given everything, and so on, like this goes on, right? If I'm actually computing the joint probability of this value. So then the word naive comes in and you just say that these are independent, right? And so what I can say is that for any like p of x sub I, given xi plus 1, and so on up to xn c sub k, is equal to the probability of finding that word given that it's spam, right? So I'm just like making a very basic assumption that each of these words are independent. The probability of getting these words is like independent from one another. And so instead of like computing each of these conditional probabilities for every word, I can simplify it, because like the probability of finding a word given the rest of the words, finding this word was dependent on the rest of the words and so on. Right, so I just like simplify that, and that's how a naive, the word naive comes in, that I'm assuming all the features are independent from one another, and then I can just like get the numerator of my classifier, which was the probability of C sub k spam or not, x1, and so on up to xn, which is then you get like this. This is going to be just like ck, which is like the total probability of the prior of getting a spam, and then all the other elements multiplied. Let's say it's not I, it's from 1 up to n, and if I remember correctly, it's going to be this term here, I c sub k, right? And then obviously when I compute, like when I actually use the classifier, I'll have it divided by the evidence, which is going to be the total probability of like having all the words. So now the point that I'm trying to make here is that this like naive Bayes classifier is like a probability model in some ways, because I'm trying to figure out this like joint probability of like whether this message is a spam or not, given all the like whatever it's conditioned on. Right, so this is the most basic example of a generative model where I'm like looking at probability distribution, although if you look at it, I have simplified it, of course, but then I'm generating this probability distribution for each of those words. And then I'm trying to like create a decision rule that based on this decision rule, so the decision rule is going to be the max of like this value, right? Is the one, if you find like the highest probability value for a given word is like, then it's a spam, otherwise it's not. Right, so that's what I'm trying to do in that, and that detail is given here in this link, so I'm not going to go into that. But I just wanted to make sure that we understand what a generator does, essentially. Right, so naive Bayes is a good example to understand what, like how these generative models work. All right. So all right, so that's that. So that's the introduction to like what discriminative models are and what generative models are, right? So then moving on to the topic for today, that's the generative adversarial networks, or GANs. And these are like two neural networks combined together. So we have like a generator and a discriminator. Both of them are combined together to achieve something. And that's something that something is what we are going to learn today. Okay. So let me jump into that. Even before we jump into the architecture, let me give you a high level like idea of like in what kind of examples and what kind of situations will we need this. For instance, so what we are trying to do is we are trying to create these high quality images, given that we have low quality images. Okay, so let me draw this here to give you an idea, and then we'll go into the structure of these GANs. Okay, so let's assume maybe I have a distribution center, and I want the images of that distribution center, and I want to keep track of like through some satellite pictures, right? And I know that I have like these low quality images and I want to create high quality images using those low quality images. So one way of doing that is that what I'll do is like in this GAN architecture is that I'll have two different neural networks. The first one is the generator, and that's where the name comes from, right? So the generator, and I'll give it some like low quality, and I'm just like writing as LQ, some low quality images. And because this is a neural network in itself, okay, so it is going to, in some ways, and we'll see what are those ways, it's going to generate these like fake images of the same, whatever that is, right, input, but like higher quality images, right? So let me call them like high quality, but I'm using a hat because these are the ones that this generator generated, right? So these are not real images, but in some ways they are fake images. And remember, I wanted to have like high quality images, but like very close to the real ones. And so in some ways, what I can do is, let's say I do have some very few high quality images for that particular, like some aerial images, right? And so I have them already. And so I'm calling them high quality, but actual high quality images, right? Not with a hat. So these are the ones that are generated. And so these are fake, right? And these are the ones that are real, okay? And there is another neural network that's known as the discriminator. And so this is a discriminator type model, and this is a generator type model. We just discussed what a generator is and what the discriminator is, right? So a discriminator is more like a logistic regression model where it's going to give me some output of like 0 or a 1. So yeah, this is fake, and this is real, right? So these are two different models. And in some ways, what we do high level is that we put them together. And the fact that a discriminator can discriminate between fake and real, we use this information from the discriminator to somehow pass to this generator, right? And so what we'll do is like we'll have the input as like the real images as well as the fake images. So we'll have like two inputs to the discriminator, and we'll perform some kind of a learning process such that like the discriminator obviously will be able to figure out like fake and real because there are some fake and some real. But we will train the network by putting both of them together such that I can propagate the loss back to the generator as well so that it learns well enough to create images that are like fake but very close to real. So it is in some ways able to fool the discriminator. So that's a high level idea. We're going to go into the intricacies of like what is the objective function and all of that, but that's a high level idea. I have like these fake images, or sometimes they're also known as synthetic images. So synthetic images is like my generator synthesized them, right? And it was synthesized from some low quality images, also known as noise most of the times. In literature, it's known as noise. And I use, so obviously when I start training my generator, I'll get like really bad outcomes. And when I feed it into my discriminator, it is going to discriminate that this is like a fake image, right? And then I'll have some outcome here. And then I'm going to do back propagation. As I pass the gradients based on that, my generator is going to learn that this is able to discriminate. And so I have to adjust something so that I generate better quality images and like keep doing that until the discriminator is fooled. That means it's able to not differentiate between fake and real, right? So essentially we are putting together two different neural networks, and then we'll see how the training works. But first, let's try to understand the architecture. So I'm going to like write the objective function and other things. Let me just use maybe this space here. This is better. Okay. So if like I think about only the discriminator, so the model that was below, that is like trying to differentiate between fake and real, right? If I think about that, the objective of that network is to maximize the likelihood that it's like able to get more and more like real images, right? It wants to maximize that likelihood of identifying real images. That's the objective of that, right? So it wants to maximize that. And mathematically speaking, I can write it something like this. So maximize the objective of my discriminator. So D is for the discriminator. And again, the way we can write this is that this is the sum of, and let me actually show you the details of, how can I get rid of this? Okay. Okay, so let's actually keep this here so that like we don't forget this. So generator, usually what happens is that you give it like, let's say like M samples of input. So like M samples are like M images, or M some like really low quality images, or it's also termed as noise because they're like really low quality images, and they're usually denoted by Z. So it could be Z1, Z2, and so on up to ZM. And okay, so that's M randomly generated samples, generator. And then I'm producing this synthetic images, M synthetic images, and I keep a hat because these are like fake, right? So I just generated them. And the way we have generated them, and I'm using the function G for the generator, right? So I've generated them using like Z1, Z2, and let's say ZM, right? So these are like synthetic images. The other thing was the discriminator. So the discriminator uses like, again, M real images, right? So let's denote them by R sub M, and then the discriminator. And then this has to just like give an output 0 or a 1, right? So I'm just like denoting that output as like D of X if this is considered X. So then like a 0 or a 1, right? That's all this is. All right, so like with this in mind, this architecture in mind, I have like the objective function for the discriminator. So I'm calling it J sub D, and I want to maximize that. You'll just see why we are doing that. So I actually want to maximize the likelihood, as I said, to correctly classify the real and the fake, right? That's what I want to do. And so the way to represent that mathematically is that I'll take the summation like M samples of real examples. So what is like the likelihood of getting them right is that my X belonging to all the real. So this is like the real images, right? Let me write it down. Real, and this here is synthetic or fake. X plus now, if you look at this thing, this here is like M samples of real examples, right? So M samples of real examples, right? And this here is like M samples of synthetic examples, right? So that's why that's what we are doing, right? So M samples of synthetic examples. And why is this synthetic? Because this thing here, and I'll show you, like they are connected as well, right? So I'm going to come to that, but like for the time being, just understand that my goal is for the discriminator, because my discriminator is also going to get these as inputs. So both of them are as inputs. Yes. Oh, yes, of course. I'm sorry about that. Yeah, I missed that. Yeah. And this, by the way, if you think about it, and we're going to come to that, is nothing but like G of Z, with Z being this thing, the noise, right? Because I'm going to get an input from this as well as the real images, right? So my goal only for the discriminator, just like forget about the generator, just think that the generator already provided us synthetic images. And so my discriminator is going to have the real and the synthetic images. And my goal here is to maximize like, and if you just look at it, when will it be maximized? If you just look at it, when will this be maximized? Just look at the elements within the log. So this is maximized when all the real ones are classified as like 1, and all the synthetic ones are classified as 0, right? So that's all. It's a very simple like objective function. So that's it. Let's say we are done with the discriminator, and then let's think about the objective of the generator now. Like, what exactly is this generator trying to do? Because the generator is not just done when we created the synthetic examples, but it's also passing the synthetic examples to my discriminator. So there's a little twist to what the generator is trying to do, right? So what we are trying to do in this one is that we do not care about the real examples. We care about how good quality are we creating these synthetic images. That's what we care about. Like, of course, I have some real images, but the generator doesn't care about them. The generator cares about how good I produce my fake images. And they should be good enough so that my discriminator is not able to discriminate between like 0 and 1. So like the point I'm trying to make is that it's not able to discriminate between R sub m and S sub m hat, right? So then thinking about the objective function of the generator, right? It's going to be to minimize this thing here. This should be minimized as much as it can. So maybe like if you've, because there is no space left, so I'll have to do this again. And like I can rewrite a few things because we will have to. But let's like focus on what the generator is trying to do. So it's trying to minimize, and J sub G is just like for the generator and the discriminator, only for the synthetic samples. X, where this is nothing but, right? So I'm here, like the objective is, this objective will be minimized when these synthetic samples are incorrectly classified as one, as real, right? Then only this will be minimized. So it's just the second part of like my discriminator, my discriminator objective. The only difference is that there I'm trying to maximize my likelihood that I correctly classify real and fake. Here I'm trying to minimize this, the fact that in some ways the generator shouldn't, the discriminator should not be able to distinguish between like real and synthetic. And so this will be minimized when my synthetic samples are incorrectly classified as one, right? So of course, like we are trying to do two different things. And then we have like these two different networks that are connected to one another. And so eventually the question arises, like, what exactly are we trying to do in this like entire thing? What is the objective function of this entire network, right? And so this is like the overall objective is known as the adversarial min-max. And so we are trying to do both essentially, right? So they are adversarial in the sense that they are working towards like working against one another. And we in some ways want the generator to win, right? And that's how we set up the problem. And we'll see like how the training process goes on that like actually facilitates that process. But first, let's look at this overall objective function, which is a min-max function, because I'm combining the min from the generator and I'm combining the max from the discriminator, right? So this is the objective function is known as the adversarial min-max. And the details of like the entire derivation are given in the paper. These networks came out in 2014, very well known. Now, like the research is, I would say, really rapid in this field as far as like these GANs are concerned and their applications are concerned. So they are almost everywhere. But these are a very recent development in neural networks, and you can actually check that paper out by Longfellow, and like you should read that. It came out in 2014. Okay, so coming back to what we were trying to do. So this is known as an adversarial min-max objective function. And what we are trying to do is we are trying to minimize over my generator, right? And I'm trying to maximize this. And here, like, let's say m samples. So I'm just like creating a cost function over all of them. And then what we just saw, the min-max, because like the second part actually is the generator objective function. And the first part is actually the discriminator objective function, right? So just like rewriting that. Yeah. All right. So what we're trying to do is this is my objective function. It's a min-max. So I'm trying to minimize over my generator and I'm trying to maximize over my discriminator. So, okay, all of that is excellent. But then how do we train it, right? That's the big question. And let's say, okay, of course we train it, but how do we accomplish this task of fooling the discriminator? Because that's the whole point of, that's what the generator is essentially trying to do. It's trying to fool the discriminator in some ways, right? So the training is an important aspect of this. High level, even before we jump into the details of the training part, if like my generator's job will be done if I'm successfully able to confuse my discriminator, right? I'll be done when my generator is able to produce such images that my discriminator is not able to distinguish as synthetic versus real, right? And so usually, so I'll train until that point. And so what is that point? That point is going to be like, let's say the discriminator's accuracy drops to 50%, right? And so if you think about the accuracy being 50% in like a binary classification problem, it's like almost equal to a random chance, right? It's real or fake, like 50% chance of getting that. And so in some sense, the training stops then, because then my generator's job is done of like confusing the discriminator enough that it's not able to distinguish between real and fake. So that's a high level idea, and that's how we train this network. But then there are certain details that we need to know, because obviously how the flow, how the backpropagation works, and how the flow of the gradients work, and when to do what. Right? So let's go back to the lecture notes. I did try to summarize them here. Okay, so here are the details for how we train these networks. The first thing is that the training proceeds by alternately updating the parameters of the generator and the discriminator. You don't update them together. Of course, like you might argue that the backpropagation, if we are doing backpropagation, we will be propagating the gradients, and that's absolutely fine. You will propagate it through the generator network and the discriminator. It's your choice as like somebody who's modeling this and using this, is like when to make the updates based on the backpropagation gradients. So that's what like I utilize in here, when to update my generator gradients versus when to update my discriminator gradients. All right, so let's go slowly over this, because I know this is a lot of information and it's hard to absorb, which is fine. So again, going back to the overall structure, the generator is going to take some noise samples, and based on the probability distribution, similar to what we said in variational autoencoders, I'm going to produce some samples, some output, right? And then instead of like, I don't use a reconstruction error, but like we saw what the objective function was, right? So that's, all of that is good. But there are two things that happen in this network, because we have like two different neural networks. Now in the discriminator, I'm trying to maximize something. So instead of using a stochastic gradient descent, I use a stochastic gradient descent to learn the parameters of my discriminator. So that's the first thing. Instead of using, it's just like a flip thing, right? Instead of like minimizing, you're maximizing something. So it's just like using the gradient descent, but like adding the values. That's it, right? And then, as always, for the generator, I'm still using stochastic gradient descent. Now, how are the, like, what is the flow of the gradients, and like what is the process? Okay, so you have to follow these two steps no matter what. So these are the two steps that need to be followed, and the first one needs to repeat k times. And I would say, like, here, be a little cautious with that k, because in most of the situations that k is just 1. So sometimes like k can be more than 1, depending on like what the problem is. But what I'm trying to say here is that usually this k is 1. Okay, so we begin with a mini batch size of 2 to the m. So remember what m was? M was the number of real images, and m was the number of like my input noise. So I take synthetic images because I generated something from my generator, and I have m synthetic images and I have m real images. High quality, low quality. But remember, the low quality are the fake images. Okay, so instead of like m, I have 2m. Why? Because m is like my high quality, and the other m is my synthesized images, right? And think that this generator was like able to create those synthetic images initially, and they're like really bad quality. I don't care, but they have like some kind of synthetic images. Maybe they are like extremely poor quality. I don't care, but that's the point I began training my network. Okay, so then so that's what this says. The synthetic examples must be created by inputting some noise samples to the generator from a prior distribution, right? And real samples, well, I have some information of the problem, and I have these, like I'm assuming that I already have those images. Okay, so that's my input. And what I'm going to do is I'm going to run stochastic gradient descent only on the discriminator, right? So I'm going to run stochastic gradient descent only on the discriminator to maximize the likelihood that my discriminator classifies the real and the synthetic examples correctly, right? So the generator doesn't come in here. I'm just training my discriminator so that it's able to classify fake versus synthetic, because I have like both the inputs. Okay, and like for each update step is like performed using backpropagation only on the discriminator network with respect to this like mini batch, right? So just like assume that this is an independent neural network. And as I said, like repeat this k times. So maybe you wanted to do it k times, just go ahead, do it k times. Usually it's done once, but maybe we need to do it more. So that's it, right? So once I'm done with that my neural network is ready. It has like it learned some parameters and it's ready to classify more, right? That's when my generator comes in. Okay, and then that's the generator was the top network. It was another neural network. And what I'll do is I'll place this discriminator at the end of my generator. Okay, and then I will provide my generator with more noise, with more like random noise samples, the input to my initial, remember the top network that in the picture? So that's what I'm going to do. I'm going to provide more noise to that. But remember, after like I've created the synthetic examples from this, I have hooked up my discriminator, which was already like pre-trained in some ways. That's also there. Okay, so once that's done, right, I will perform this like stochastic gradient descent on the parameters of the generator to minimize the likelihood that the discriminator correctly classifies the synthetic example. So remember the minimization objective function. Okay, so here I'm passing my gradients. I'm passing my gradients of my discriminator into the generator. And the generator is trying to learn and create new synthetic samples based on these updated parameters. Although the backpropagation is going to propagate the gradients in the discriminator as well, but I'm not going to update my discriminator until like this one step is done. Yes. Yes. So that's why I think I said provide the generator with like more M noise inputs again. Yeah. And so like the generator, so the whole point here is that the generator is going to get better and better because I'm passing the gradients from the discriminator. Because like, let's say it created a synthetic, a picture that was fake, and then the discriminator correctly classified as fake. And so the objective of my generator was the opposite. It wanted the discriminator to not classify it as fake. And because I'm passing the gradient through the generator, it updates the weights accordingly. And so the updates will happen accordingly because the objective of my generator is like flipped this time. It doesn't want it to do what it's doing right now. That's it, right? And so that's how like this training will go on. So usually like this is done once. And then again, I'll perform the k steps. The only thing that's happening between these two steps alternately is that you don't update the parameters of each model in every run. So once you update the generator, then you update the discriminator and so on. And so like you keep adjusting. And the fact like this name adversarial comes from the fact that both have like an opposite objective. My discriminator is trying really hard to correctly classify between synthetic and real images. And my generator is like going in the opposite direction. And it's trying to minimize that likelihood, right? It's trying to minimize that likelihood. So in some ways, it's more like a game that's there in between, like who wins. And then depending on the data, depending on the problem, usually then, as I said, the stopping point is when the discriminator starts like when the discriminator accuracy falls up to like 50%. And then it's just like random chance, right? 50% is anyways, if I just pick an image and say it's fake or real, that's 50% accuracy anyways, right? So that's the whole idea of like these GANs. They are pretty, I would say, popular right now for a lot of problems, specifically problems like these where you don't have, like if you think about it, it's an unsupervised learning uh, model, because we don't have a lot of labeled data, especially in like computer vision type problems. So this helps in some ways because I'm here like able to create these fake images or like fake data, which is as good as real. That's what my generator is doing, right? It is creating those synthetic images that are really high quality. So like instead of getting like real images and labeling them, this is a far better technique, a far better method, right? So let's quickly jump into this. And okay, so I have some more. Yeah, so I already talked about this step. Yeah, the value of K. Now, if we go back to this step one, right? And I said that I have a mini batch of size 2M created with equal number of like real and synthetic examples. And then I input them to the discriminator, train the discriminator network. This can be done K times, usually like in most practical situations. If K is like less than 5, that's good. Usually K is 1, and that's also fine. So it's like alternating between like the discriminator and the generator once every time. But you can have like this step repeated K times. And so that's what like this is showing. And then the iterative process is repeated until convergence. This has been shown to have like achieve a Nash equilibrium. I'm not going to the math side of things. Like thinking about that as like a 50% accuracy is a good, I would say, analogy to this. All right. So that's GANs. I would definitely jump into the paper because that's, I think like I highly recommend everybody read this paper, this one that actually introduced these networks. Generative adversarial nets, and let me show you they have okay, this is not the one that has the conditional one, but regardless, they have performed like more than one experiment to show like how they are generating uh, images, high quality images from some like input noise, believe it or not, right? So these are some of the like visualizations of some of their experiments that they performed. It's not a very long paper. I think I've talked about like most of this. So here is the exact algorithm. So you can just like quickly go over that. But obviously, like we do understand like high level what's going on, right? Okay, so that's that. Then the next thing that I wanted to talk about today is conditional GANs. So then rest, like as long as you understand the adversarial notion, as long as you understand the min-max idea of these GANs, the rest of their like variants are pretty easy to understand. So like, for example, there are cyclic GANs in which you put like more than one GAN network one over the other, and then they are interacting with one another. Yeah, believe it or not. So there is that. And like all these like deep fake videos that you see have in some ways or the other like these GAN networks somewhere. But yeah, they're cool. They have like these cool applications where like you might just go and create some like fake videos of celebrities and so on, right? So you must have seen those on social media, right? But yeah, going back to conditional GANs. So here there's a slight update to the traditional GAN architecture in the sense that in both the discriminator and the generator, I'm also providing some additional inputs to it. For example, it could be a sketch of some image, and then I'm trying to output, like I'm trying to create a real image out of that, right? Or maybe some tags, right? For example, a smiling girl, or maybe some like bad quality image, right? And then that's an additional input to my generator. So let me just like quickly go over this, because I think we have time, and today's lecture is not that long. So, okay. So here, I'm just looking at the generator. In this like conditional GANs, my discriminator will stay the way it was, right? It's trying to just like differentiate between real and fake, right? But instead of like only having noise as an input to my generator, I also have some conditional input. For example, in addition to noise, I have the some artist sketch of a picture, and I'm trying to create a real picture out of it, right? Sometimes we have that, right? These are known as like paired inputs. paired input output, because like this artist sketch actually is for this photograph, right? Or sometimes you might have like a low quality image, as is the example here, right? So you have a low quality image. That's so essentially my learning in some ways is better in this case, because like in addition to noise, I've conditioned my learning on these extra additional inputs, right? So maybe my generator will be faster in generating like these outcomes. So that's what conditional GANs do. And again, there's a paper on like how they are trained and other things. But again, the high level idea stays the same. It's still the min-max adversarial min-max objective. And I'm trying to fool the discriminator by generating better samples every time. So I'm trying to minimize the likelihood that a generator is able to differentiate between real and fake images, right? But I have provided more information. So in these conditional GANs, they're better at like creating these synthetic outputs, and they're faster as well. But again, I would say there is a downside, because like you need these for that conditional thing, you need these extra inputs, right? Because like in my very basic GAN, I'm just like utilizing this noise and I'm creating like some synthetic images. So it comes with this price. Let me quickly go to, I think I have a paper that talks about this. Conditional, or maybe not. Yeah, I don't remember I got the paper. Yeah, I tried to search for that. But yeah, I think the idea is clear to everyone, right? That's what like conditional GANs are doing. Okay, the third, and I think the last one for today, and I'll go over rec GANs quickly, but they're not that important from the perspective of like understanding the architecture. In addition to like GAN networks, and quite often used now, are cycle GANs, right? So again, there are like multiple GANs put together. So like the simplest way of thinking about them is that you have like two different GAN networks, and they are interacting with one another. But then the question arises, why do we need to do like that? And like what kind of problems we need to do that? So let me show you the paper on this one. I think it's paper number 2. No. Yeah, it's this one. And here it shows why we need these cycle GANs. Now, notice like the first one, this one here. Let's say I'm like, so these are known as paired input output, like paired training data. Why? Because like I'm showing like a picture of a shoe, and then there is like a real picture of a shoe that I want as an output or something, right? So this is like paired in some ways, it's the same thing. But unpaired means that like you have different images, and so they're not like matching if you look at them. And so I need to somehow, like this is unpaired data, and you need to somehow extract some features from this. So for example, whether like what's the weather like, or like what's the overall like where like the overall scenery is like, and things like that, right? So you need to extract that. So in case of like unpaired training data, how do we like with no information provided as to like which X matches which Y in like a situation like this, how will we train our network, and how do we get like the outputs? So one quick example of these type of problems is that, let's say I'm giving you some landscape pictures of summer, and you need, and I want you to generate some landscape pictures of winter, and they are like different from one another, right? So different pictures, that kind of an example. So how are you going to do that? Because like in the architecture that we just saw, we are doing something like this, right? I'm giving you some input, and you are creating a high quality output, which is similar to what's in the like my input. So for that, we use these cycle GANs, and this is the high level architecture. And one way to think about this is that you have two GAN networks, right? GAN 1 and a GAN 2. And let's say like, let me write it down here. Okay, so what I'm trying to do is I have like two collections. So collection 1 is like landscape summer, and collection 2 is like landscape winter, but they don't quite like, it's not the same scenes. There are some different landscapes. And so let's say I'll take one picture from collection 1, right? It's the summer landscape. And then you might have noticed like the way those like the colors and everything appears in pictures that are like from the summer versus winter is like different, even for the same scene, right? And so you have different scenes from two different seasons, and you're trying to like somehow translate this summer to winter or like the opposite, right? So that's when you need like these cycle GANs. And what you do is like in GAN 1, so you'll have like two GANs and they are like connected to one another. And the objective is a little bit different. It is known as the cycle consistency loss. And you're going to see in the paper like how they've defined it. But regardless, what this is doing is that in GAN 1, you'll have a generator and a discriminator. And in GAN 2, you'll also have a generator and a discriminator, right? So a generator and a discriminator, right? And what you'll do in the first one is that in the generator, you need an input, right? And then there has to be an output. So what the generator does is that it takes photos of summer from collection 1, and I'm calling it COL1, right? And I wanted to output photos of winter, right? So that's what I wanted to do, right? So I wanted to output and remember the winter photos are in collection 2, right? And what the discriminator does is that this takes photos of winter from this collection 2, right? So the input here is this, but the actual one, right? So the real example. This is the output that the generator just generated, right? But here I'm going to take the real pictures from collection 2 and then train on like it's going to discriminate the likelihood that these are these are from collection 1 or collection 2. And so it should be like the likelihood that the image is from collection 2, and then that should be 1, right? And then I'll do the same GAN thing that I'm trying to fool the discriminator. And the exact opposite is done here, right? And what happens is like the exact opposite, meaning the input is going to be winter, winter, collection 2. And the output is going to be summer, collection 1. And the discriminator will take real images from collection 1. And then these two are interconnected, so that like my generator in my first network learns from this information as well, and it's able to generate like images from some other season and some other landscape. Again, I don't want you to like memorize all this or remember all this. Just remember that putting two GAN networks that are interconnected to one another such that one of them is learning to fool its discriminator for like one collection, and the other one is fooling its discriminator to discriminate for the other collection. If they are interconnected, then we will be able to generate images from one collection into another with the different landscapes. And so this is the exact thing that they talk about in this paper. And actually they show you how they're doing it. Just the one. So here, like it contains two mappings, as I said. So like this is like the first one. G is, so they're actually, they're saying that this is the entire model, and this is the second, like GAN 1 and GAN 2, right? And so this is like the forward G mapping is from X to Y, and the backward mapping is from Y to X. So this is like the GAN 1, and this is the GAN 2. So again, this is used for image-to-image translation. That's the problem. So if you have a problem that needs to have image-to-image translation done, or sometimes even things like these. Let me show you. So this here is a nice example of like why we need this cycle GANs. And for example, like here is a picture of like I think a summer and then winter. Or maybe like look at this, zebras versus horses. So it's the same landscape, but maybe like summer, winter, and then instead of zebras, you have horses. So basically a lot of attributes are the same, but a lot of attributes are not. And so in problems like these, we like image-to-image translation, that's what this problem is known as. We use these cycle consistent adversarial networks. One thing to remember though is that the objective function changes a little bit in this problem, given that we have done something to the overall architecture. And this paper describes like what that is. As I said, it's known as the cycle consistency loss, right? So it is going to calculate the difference between the image input to GAN 1 and the image output by GAN 2. And the output by output, I mean the synthetic image that the generator has created. Okay, so that's why it's a little different from the loss that we talked about earlier. So they actually show you here. So this is what the adversarial loss is, which we are familiar with. And this is the full objective functions. Of course, like I don't want to jump into the details of this, but high level, that's what this is trying to measure. The difference between the input to GAN1 and the difference in the, so in some ways, this is like the reconstruction error, the one that we talked about earlier when we talked about autoencoders, right? So in some ways, it's that. Okay, so going back, let's quickly go over RecGANs because today's lecture is not that long, so I will quickly show you what these do. And these are mostly used for recommender systems. Again, this is a nice paper if you would like to read, optional, I would say, but please read the original GAN one. That's like really informative. This one actually has utilized GANs along with recurrent neural networks to learn the temporal problem for recommender systems. Okay, so a lot of words there. Let me just like explain what that means. So in recommender systems, there is this problem of like this temporal recommendations, meaning with time for every user, the recommendations and everything gets affected, right? So what like some point in time you have different user preferences versus like some future point in time, right? And so in order to utilize that idea, what they're doing is they are utilizing GANs along with recurrent neural networks. So they've combined both of them in a way. And so that's what this paper talks about, like the and they're calling it RecGAN framework, in the sense that the generator and the discriminator both are different recurrent neural networks. So I still have the generator, I still have the discriminator, but they both are RNNs. And so you can imagine that the training of this network, and of course we know that RNNs are like, we train them using back propagation through time. They still do the same, but then obviously it adds complexity to this model, right? So essentially you have two RNNs that are interconnected to one another, with one being the generator, with the other being the discriminator, right? So that's what this paper talks about. I really like this thing because I think this is one of the first papers, or like one of the few papers that like in the recommender systems research or in that space, they're using this like idea of like min-max type of a game. So that's that. And I think that's also required because of the dearth of like data in recommender systems space, specifically like user data, user preference data. So that's why this is like such an important, I would say, paper here. But yeah, the objective is again like the min-max, and they're trying to capture the context of choice or context of preference for users using this idea. Okay. So again, there's no need to get into like the details of this, but just like be aware that this exists, right? This is an important paper. Okay, I think I had a quick another one before we end today's lecture. And this one actually shows how we can use GANs for CNNs, with CNNs, and how we can use them. And so this one is known as like a DC GAN generator that's used for like scene modeling. And this has like multiple like these convolution layers, and like we are aware of like these intricacies here, but this also uses a GAN type of a network, if I remember correctly. So they do use that to generate like these high quality images. Yeah, so they're here, like they talk about like how we can utilize that. And obviously the generator discriminator architecture is more suited for these kind of problems, specifically for creating like these images, high quality images, data augmentation, and so on in computer vision. So this paper actually talks about like how we can utilize the GAN framework for like computer vision type problems. And finally, before we end the lecture, there is this like a link that I've provided how to implement them, how to implement these DC GAN, the one that we just saw in the last paper, using this adversarial network in TensorFlow. So this one actually uses MNIST, if I remember correctly. Okay, and this also talks about like what are GANs and how do we implement them, but I think now we are clear on what are these. And yeah, this one actually really gives a good like visualization of what's happening, right? So here is the generator with noise. right? And this is like the discriminator is able to discriminate, obviously, that this is not a cat, right? And then many attempts later, the generator has some synthetic image. Again, the discriminator is not fooled, but eventually the generator is able to come up with a very high quality image, and the discriminator is fooled into thinking that this is a real image, right? So this is a very nice, I would say, demonstration of what's really going on in generator and discriminator type models. Okay, anyways, this notebook actually demonstrates how you can use this entire process with MNIST data. And so they began with like some noise, and they actually are able to generate like these high quality handwritten digits pictures, right? So this talks about the implementation and how to do that step by step. So taking a look at this would like be really helpful. All right, so as I said, today's lecture was short, so that's all. And I know that this is a lot of information with GAN, so I don't want you to like overwhelm with like more information. So that's it from my end. If you have questions, you can ask. Otherwise, yeah, that's it. And thank you so much. Yeah, in terms of announcements, you'll have homework 5, or you'll see homework 5 sometime today.